Good day to the external examiner, TS Dr. Siva, internal examiner Dr. Shafira, and my project supervisor Dr. Bawadi. My name is Frederick Chong, and I'm majoring in the process analysis and control. The title for my final year project is Predictive Modeling for Base Oil Properties, and this is a collaborative work with the Petronas project team. Here's the flow of my presentation. I will first introduce the background of the work and then screen through my findings from literatures to assess key predictors and suitable algorithms for this task. Following that, I'll brief through my methodology in conducting this work and its results. And finally, concluding my presentation with a summary and few recommendations. In this section, I'll run through the background of this work, its problem statement, and subsequent aims, as well as the scope of this work. To begin with, what is base oil? Base oil is basically lubricants without additives. Base oil may have multiple grades, which are mainly defined by some of these key properties. KV100 stands for kinematic viscosity at 100 degrees Celsius. Noack, which is a measure of volatility. VI stands for viscosity index, which measures the tendency of the base oil viscosity to change with temperature. CCS stands for cold cranking simulator, which measures the apparent viscosity of base oils under low temperature. And finally, pour point, which is the temperature where the oil will solidify due to the presence of wax. The base oil production process can be categorized into three main sections: CDU, crude distillation unit; VDU, vacuum distillation unit; and MG3, which is the refining and finishing section for base oil production. The raw crude oil enters the CDU at atmospheric pressure to fractionate the raw crude into a variety of products. The bottom residues of CDU then enters the VDU to further break down the heavier hydrocarbons at vacuum conditions. Now the three side draws coming out from the VDU will enter the MG3 section for treatment to meet product specification. Given the background knowledge of this work, here's the problem statement. Due to the pandemic, there has been much fluctuation in the lubricant market. This drives the need to optimize the base oil production process. Secondly, the standard process simulators cannot accurately model the lubricant due to the presence of waxy solids. Moreover, lab analysis for base oil property measurement is time-consuming and costly. All these give rise to the need of this work, which is to develop a predictive model to predict ahead of time the base oil yield and properties, which then allows necessary actions to be taken. Thus, the main objective here is to develop a statistical model to predict the base oil yield and other properties based on CDU, VDU, and MG3 data. This means ultimately we want to predict W directly from X. Secondly, the aim is to optimize the developed models to improve the prediction accuracy and precision. Thirdly, it is to determine suitable algorithm to develop the prediction models. Thus, the scope of this work is to integrate the individual models of CDU, VDU, and MG3 into a single model, thus being able to predict W from X. Subsequently, tune the model hyperparameters to their optimal values, and following that, the prediction performance of various algorithms will be compared and assessed. Hence, by developing, optimizing, and selecting an appropriate model, the problem statements can be solved. In this section, the key predictors for each base oil properties and a comparison of various machine learning algorithm performance are being reviewed. For KV100 and VI predictions, past studies shows that the density and oil structural parameters such as branching number are key predictors, obtaining R square of over 0.95. Moreover, SIMDIS is said to correlate strongly with Noack. Next in line is the prediction of cold cranking simulator. Sapao and his team found out that the oil structure, particularly isoparaffinic carbon structures, affect the CCS quite significantly, obtaining an R square of 0.88 using a simple linear regression. For base oil yield prediction, again, the hydrocarbon structure have considerable impact on oil yield with a correlation coefficient of 0.84. Finally, the hydrocarbon structures once again shown to be strong predictors for pour point, obtaining an R square of 0.93 using the multilinear regression. Besides, another work used the principal component method and analyzed that the wax and asphalt content and kinematic viscosity are strongly correlated to pour point. In summary, the oil structures have been shown to be the key predictors for most properties. Next, we shall compare various machine learning algorithms' performance in the prediction of dead oil viscosity. This framework compares 5 learning algorithms, and overall, in terms of R-square measure, superlearner outperforms other learning algorithms, while XGBoost gives the lowest error among all the learners. It is worthwhile noting that no one algorithm is definitely better than the other in prediction performance. The algorithms used is largely dependent on the data set, and some algorithm will fit better for certain data set but not the others. In summary, there have been many researches done on these learning algorithms, even in the petrochemical industry, and attain a moderate to high accuracy of prediction. Thus, it is feasible to predict likewise the base oil properties. In this section, I'll walk through the methodology of developing a predictive model and the tools that are used. Here's the adopted methodology in conducting this task. I've segregated them into 4 main phases denoted by the 4 different colors. The first step is done by the Petronas project team. Using R programming, then the data set is read and stored. And then some preliminary data processing steps are done, such as filtering of outliers. We now then have a good data set for analysis to begin with. And the first step in the analysis is to screen through the correlations of the process parameters with the targeted response using various statistical functions such as multivariate methods. With these functions, we then shortlist the predictors and form a new data set with a targeted response. Then split the data set into training and test set in 70:30 ratio. The next phase is the model development phase using the XGBoost and the light GBM algorithm. The hyperparameters are tuned to prevent overfitting or underfitting of the model. Then using the tuned hyperparameters, we formulate a new model and retrain the model. The last phase is the model validation phase where certain statistical measures and diagnostic plots are reviewed. Then an importance plot is also generated featuring the rank of importance of each predictor. Next, I shall present the outcome of this work, which entails a prediction performance for base oil properties and a comparison between 2 learning algorithms. Firstly, the prediction of KV100 using the gradient boosting machine algorithm. With these specifications of model hyperparameters, the model is trained and validated and subsequently tested. The outcome of the model is shown on the right-hand side, where the R-square of the test set is 0.876, which is relatively good and fulfills the benchmark set by Petronas. An observation that is worthwhile noting, there seem to be 3 clusters from the plot, where KV100 is seen to run at 3 distinct ranges of set points, which I suspect to be 3 different grades of base oil, which may also explain why the data points that are out of these 3 clusters, as indicated by the red color points, tend to have poorer prediction. These red points are suspected to be outliers or grade transition data. Overall, the prediction for K100 using the GBM algorithm is considerably good, with the wax density as the key predictor. However, the grade code data is also required for further analysis to ensure a better performing model. Using the same predictors, but now the XGBoost algorithm with the following hyperparameter specification, an R-square of 0.871 is obtained. Besides, visualizing the residual plot may indicate the model performance. If the data points are randomly scattered along the x-axis, this may indicate a good fit. However, if a certain pattern is observed, as in this case, then the model may be less desirable. Comparing the GBM and XGB algorithm for KV100 prediction, GBM used a slightly better result. Next up is the prediction of Noack volatility. With the following specifications, the model is trained, and the actual by predictor plots here seems to fit nicely for this case with a test R-square of 0.845, which is considered good. The simulated distillation in this case is the key predictor for Noack, which agrees with the presented literature and the fundamental chemical engineering knowledge. The same observation is noted here, where there are 3 clusters of data in each of these plots. And when plotting Noack against KV100, 3 clusters of data can be seen, which again is suspected to be 3 different base oil grades, and the red data points in between these clusters are presumed to be outliers of grade transition data. Hence, the grade specification data of the base oil is required to deepen the analysis. Now, using the XGBoost algorithm and similar predictors, an R-square of 0.866 is obtained. The actual by predicted plot also seems to fit better in this, as well as the residual by predicted plot. The key predictor used for this algorithm turns out to be the hydrogen inlet pressure over feed. This may be due to the different hyperparameter tuning that result in different variable importance. Overall, the XGBoost algorithm performs slightly better than the GBM for the prediction of Noack. Thirdly, the prediction of viscosity index using the GBM algorithm, an R-square of 815 is obtained for the test data set with Paul point as the key predictor. For the case of VI, it is observed that there are 2 different clusters. Again, not much can be explained unless we have the specification data. Using XGBoost with similar predictors, a significant improvement with the R-square of 0.903 is obtained. The residual plot indicate that the model is performing well as the data points are randomly scattered along the residual equals to 0 line. Here we also observe that the data points in between the clusters have poorer prediction, and this may be the great transition data. Overall, the XGBoost performance is significantly improved compared to the GBM in the prediction of VI. Moving on, the prediction of co-cranking simulator. The test set shows an R-square of 0.832 here, which is relatively good, given that CCS is a difficult parameter to predict. Only one MG3 variable is used in this prediction, which is SIMDIS, contributing up to 48% to the prediction. For this property, I filtered out the data points that are beyond 10,000 so that the prediction is improved. Besides here, there is a string of data that is constant, which is unusual and maybe faulty data, thus requiring further verification. Perhaps an improvement that can be made here is to segregate the data to a few different modes, covering a few ranges, because if the range of data is too wide, prediction tends to be poor and weak. The XGBoost algorithm, on the other hand, performs quite poorly with the same predictors. Visualizing the residual by predicted plot, a notable pattern can be observed, thus indicating a bad fit of the model. Variable importance is almost similar to that of the GBM, but XGBoost only yield a R-square of 0.78, making it a weaker learner than GBM for the prediction of CCS. Thus, for this case, the GBM wins. Now, moving on to the fifth parameter prediction of base oil yield. Using the GBM with the following three specifications, a test R-square of 0.82 is obtained. The actual by predicted plot also seems to fit nicely overall, with a few data points in exception. The key predictor here, after some analysis and trial and error, is found to be the wax density. For example, using the partially square method to generate the variable importance in projection VIP plot, SDWO density occurs to be the most significant predictor among all the other MG3 variables, since it has the highest VIP value. When plotting SDWO density and yield on the same graph, it can be seen that when the wax density decreases, as indicated by the blue trend, the base oil yield also decreases. Thus, based merely on the data, it seems that the wax density has a strong correlation with the base oil yield. This, however, must be verified with a contact engineer. Now, using the XGBoost algorithm, the overall fit does look okay, and just that the data points that are having yield below 0.5 seems to have poorer prediction than the higher yield data points. In the order of significance, somehow the algorithm reads that SIMDIS is the key predictor instead of wax density. The XGBoost yield an R-square of 0.65, which is notably poorer than GBM. Thus, GBM is likely to be the suitable algorithm for the prediction of base oil yield. Finally, the prediction of pour point. This is the most difficult property to predict and the only one that can't seem to obtain a satisfying accuracy after countless of trials. The R-square obtained for the test set using the GBM algorithm is 0.37, with the key predictor being SIMDIS. Now, using the XGBoost algorithm, the R-square for test set is 0.27, which is even lower than GBM. The two diagnostic plots here also indicate that the prediction performance is very poor. More study and analysis is required for this property, and perhaps pulling other data that correlate better with pour point. We have now reached the conclusion of this presentation. In summary, this work from Petronas is to develop a predictive model using statistical or machine learning methods to predict the base oil yield and properties by integrating CDU, video, and MG3 models. Then optimize the model by tuning the hyperparameters, and lastly, trying out other algorithms and compare and assess their performance. The outcome of this work seems to favor the GBM as the more suitable algorithm to predict the base oil properties, with an exception for Noack and viscosity index. Overall, the prediction performance satisfies the criteria set by Petronas, which require an R-square of 0.8 and above, only pour point being the exception here. Few recommendations that came to mind while conducting this task. Firstly, as seen in many cases just now, additional data is required for more in-depth analysis. Secondly, discuss with the site contact or technologies specialists to verify if the selected predictors are suitable. And furthermore, ensure that the data sets are time aligned as video and MG3 data sets were pulled separately. Finally, explore the usage of artificial neural network as a mathematical model for inferential control or model predictive control applications.
With this, I conclude my presentation. Thank you.